Okay, good afternoon, welcome. Let's continue with where we left off. So far, we have seen applications of op amps in various negative feedback circuits. All these circuits had no memory in the sense that the output at a certain time is only dependent on the input at this particular time, right? Because all the feedback networks that we considered were all only resistive, which had no memory. We also assumed that the op amp works instantaneously. As we will see going forward, that's not quite true. But we would like to begin with feedback networks where there is memory. But before I do that, I'd also like to point out that we've seen a negative feedback circuit so far, but it does not mean that positive feedback is useless, right? It's very useful, in fact. And let me quickly give you a motivating example. So we have seen already that the characteristic of the op amp is something like this. So assuming dual rail operation, if I plot V1 minus V2 on the x-axis and VO on the y-axis. Now, with V1 minus V2 being the same scale as VO, what will I get? I will get a signum function because, well, the op amp is going to saturate for inputs greater than a very small delta, and likewise is going to saturate at the negative rail when the input is slightly negative. Now, so this this characteristic itself as such is useful because it helps you figure out whether this characteristic is that of a comparator. So basically, when the input V1 minus V2 is less than 0, you get a negative rail output, and when the input V1 minus V2 is greater than 0, you get a positive. Now, one practical problem with this is that whenever there is, you're basically trying to compare two signals and figure out which one is greater. And sometimes, it more often than not, it so turns out that when you're comparing V1 minus V2, there's also some some extraneous noise that's present, right? So ideally, what you're so basically, what will happen is that this V1 minus V2, this is time now, and this is V1 minus V2, right? And so basically, there's let's say the input is close to 0, but right, or maybe slightly more than 0, but there's sometimes or more often than not noise riding on that difference. And if this goes directly into the comparator, what happens? Well, the output sometimes is like this, then it goes down, goes up, then right, goes down again, goes up. So this is there's a lot of what do you call chatter, right? Simply because of noise. Technically the input may be very small and positive or very small and negative, right? Ideally, the comparator should show either the positive rail or the negative rail, for extended periods of time. But because of this noise riding on it, basically it either goes to the positive rail or negative rail and keeps jumping between the two rapidly, where we know that rapid jump is not really shouldn't be there, right? So ideally, what do we want if we know that the input is slightly positive, right, and it is this noise which is basically causing the effective threshold to get crossed, right? And the threshold, this is threshold, is 0 volts, right? So if the input is small and positive, correct. The noise on the input is basically causing the difference to cross the threshold, and that is why the comparator is firing and going to the output of the comparator is going to the negative rail, right. So, basically for small positive inputs, noise causes V1 minus V2 to go below 0, which is basically the threshold, once in a while, and this leads to chatter, correct. All right, and likewise for small negative values, what happens? Noise causes V1 minus V2 to go above 0, and again the output which should ideally have always been the negative rail, now once in a while crosses becomes the positive rail, because the threshold, I mean the input as difference has gone up above the threshold due to noise. Okay, I mean I am saying noise, but it could be some small extraneous pickup due to capacitive coupling on the wires. Anything is possible, right? So, basically, whenever the input is close to a threshold, then you will always have this problem of any extraneous effects, noise, maybe disturbances, etc., can cause the effective input to go above, just cross the threshold, and then you have. So, how do we fix this problem when the input is very small and positive, for example? So, how do we fix this? So, the solution therefore is that when the input is small and positive, what should the what will the what should we make the threshold? Pardon? I mean, when the input is small and positive, what would be? I mean, if the threshold is basically what do you call? The problem is that the threshold is the threshold is very close to the input, and that's basically what is causing the problem, right? Okay. So, when the input is very far away from the threshold, it doesn't matter if the threshold moves, because when you add noise and so on, or even if you deliberately move the threshold, if the input is far away from the threshold, it doesn't matter, correct? Okay. It only makes a difference when, I mean, the problem that you are trying to avoid is that small positive. We know that the input plus noise occupies a certain window, correct? Okay. I mean, ideally the input is like this, supposed to be like this. In reality, on top of it, this there's something riding, okay. But we do not want the comparator or whatever decision we make, we do not want it to respond to, I mean, if the, once the input crosses 0, right, or the comparator declares that the input is one level, right, whether it is plus or minus, it does not matter. Okay. If when the input comes down a little bit momentarily, the comparator should not switch decision, because we should know that this small jump is actually due to some disturbance or noise. Okay. And so, for example, here let us take this example. So, this is an example of an inverting comparator, right. So, this is V1 and this is V2. So, V2 greater than V1, what happens to VO is, let us call this plus VDD, and this is minus VDD. VO is minus VDD, okay. And if V2 is less than V1, VO is plus VDD. Now, when V1 and V2 are close to each other, then we have this potential for chatter in the output, because the difference is very small. But what we want to do is, once we declare V2 to be greater than V1, right, a small, I mean, or the other way around, a small change in V2 should not lead to the output being being interpreted as what do you call the output as being interpreted as being the output should not change from plus VDD to minus VDD, or vice versa, depending on what, right. So, one way of doing that is to basically use positive feedback. So, for example, we know that the output is either plus VDD or minus VDD. So, if we know that the output is plus VDD, that means what? The input is greater than 0. I mean, so if the output is plus VDD, we know that V2 is less than V1, right? Okay. So, and we want to make sure that a small change in V2 should not basically cause, if V2 goes up just a little bit, we do not want the output to change sign and go to minus VDD. So, what should we do with the threshold? We have to boost the threshold up a little bit, right, so that if we know that the input V2 is only mildly greater than V1, right, okay, so that noise on V2 or V1 can cause the output to change sign. How do we prevent this from happening? The moment you know that V2 is greater than V1 by a certain amount, right, what we can do is we can go and increase the threshold by increasing V1, correct, okay. So, and how do you increase V1? Well, we know that the output is, if the output is positive, then we must increase the threshold. So, you must feed back a positive quantity. So, basically this, so what you could do is basically add f times the output like this, right, and therefore, this should ideally have, so in this case the input V2 is being compared against, it's being compared against a fraction of the output, which is either plus VDD or minus VDD. So, just make note that f is greater than 0. So, this is clearly positive feedback, correct. And if we plot the characteristic, what do we see? Let us say the input was V2 was very large, and positive. Okay. What comment can we make about the output? The output will be minus VDD. All right. And the output, and so if V2 is very large, the output is minus VDD. So, what will this voltage be? Minus F times VDD. All right. So, when will the comparator switch sign now? What should V2 be so that the output flips sign? Minus F times VDD. So, you can basically the output will go all the way up to minus F times VDD. Okay. And then what happens? The output jumps up to VDD. So, we are going from the negative side here, it does this, and then it goes this way. All right. Now, when suppose we now bring the input back from large negative values to positive values. So, what happens now? What is the output now? Output is plus VDD. So, how much must the input what must happen to the input for the output to flip from plus VDD to minus VDD? Pardon? Yeah. So, the input must go as high as plus VDD. All right. So, that you basically get, so this is F times plus VDD and this is minus F times VDD. So, this is basically a way of so for example, the F times VDD, this phenomenon is called hysteresis. And the hysteresis window is controlled by this number. Of course, depends on VDD, but also but is controlled by that parameter F, that how much you're feeding back, right? Okay. So, so the input, let us say V2 was slightly less than 0. It started off, what do you call? It started off at a large value of V2, and it was it was at it is now brought down to 0, correct. Then what comment can you make if V2 changes a little bit, right, due to noise or pickup or whatever? What comment can we make about the output? The output will still be at minus VDD and will not chatter, right, right, as long as the noise plus V2 stays within that window, correct. So, it will only switch to, the output will switch not when it crosses the threshold. The nominal threshold is supposed to be ideal. Without feedback, the threshold was 0, correct. Now, what are we saying? If it has to go negative, the output should not merely, the input should not merely cross 0, but it should cross, it should go a little lower, so that we are sure that it is actually negative and it is not some artifact of noise, right. Likewise, when the input is going starting from the negative side and going positive, for very small amounts, I mean, we want to be sure that the output doesn't switch sign unless the input is actually confirmed to be positive, and it is definitely, at least we know that, or we think that it has to be greater than a certain amount to be considered positive.